In this lesson, we're going to take a look at Coulombs Law. Now, Coulombs Law takes the form F equals K Q1 Q2 over R squared, where Q1 and Q2 are the magnitudes of charge. So sometimes you'll see this written in absolute value. And so what's important to note about this is Coulombs Law will tell you the magnitude of a force, but it can't tell you which direction that force acts. Now, this is between two charges, 2 point charges. So if I have a charge here, Q1, and I have another charge over here, Q2, which way do those forces act? Well, that's an interesting question, and it depends on the sign of the charge. If these two charges are the same, remember, like charges repel, and so there will be forces this way and this way. But if these charges are opposite, if we have a plus and a minus, then these will attract, and we'll have forces towards each other. And because Newton's third law still applies, the force that this charge puts on this charge is the same as the force that this charge puts back on that charge, and in the opposite direction. So this tells us the magnitude of the force, but the direction of the force really has to come from your diagram. It has to come from the sign of your charge. Now, what are these quantities? Well, Q is, of course, charge, and that's measured in coulombs. R is the distance between the charges. That's distance measured in meters. K is the constant that allows this to be an equality instead of a proportionality. For our purposes, for our units, we're going to use 9 times 10 to the 9th Newton meters squared per Coulomb squared. Okay? That's a really big thing. So are you going to end up with really big forces? Well, perhaps, but maybe not. The charge of an electron is very small in terms of coulombs. So you might have thousands of electrons, but remember the charge of an electron is 1.6 times 10 to the negative 19th coulombs. I guess it's negative that because electrons have a negative charge. So your charges that you're dealing with might be fairly small, but because this constant of proportionality is so large, you still might deal with some fairly big forces. This actually should look fairly familiar to you. It looks a lot like Newton's law of universal gravitation, which is F equals m1 m2 over r squared times g. Of course, here g is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. M1 and M2 are, of course, the masses, and R is, again, the distance between them in meters. Notice that that is a really small constant of proportionality. That's because the gravitational force is really, really weak. It takes a lot of mass before we notice a gravitational force. It does not take very much charge before we notice the charge between two forces. The other major difference between these, gravity is only attractive. Masses only want to pull together. So we know if we have two masses, the gravitational force is going to pull them together. But with charge, it depends on their sign. If we have like charges, if we had plus plus or minus minus, they would repel. If we had plus minus, then they're going to attract towards each other. So you do have to pay attention to that. After that, it's just a matter of plug and chug, get your information, solve for whatever you need. Remember, K is a constant, but you do then need to make sure that when you're using 9 times 10 to the 9th, your charges are in coulombs and your distance is in meters. And oftentimes will be given to you in centimeters or even millimeters because charges are often not separated by large distances, whereas masses we saw generally are.